Okay, children, big day today. We're doing 8.6, which is common logs. We're going to take a lot of log ideas and type them all together. I'm going to start by taking these three properties that we've discussed and just kind of showing you an argument for why they're true. Here we have log base b of x, log base b of b to the x equals x. Basically meaning if the base of the log and the base of the power are the same, they basically cancel and you get an x. I've said the word base a lot. If you were to convert this right now is in log form. If we were to convert it, we would get b to the x equals b to the x by doing the circle thing, which clearly shows that x must be x, which is a true statement, which implies that these are true statements. It's a tautological argument, but live with it. Here, this right now is an exponential form. If I want to take it and put it into log form, this is my base. This right here is the exponent, so that's what the base is equal to. And so this is my other number that goes inside that little function slot. And then you again get that x must equal x, so if this is true, these are true. The third one is a little bit tougher to explain. We've talked about this property here. It says that log base b of a times c is the same as log base b of a plus log base b of c. Well, it gets confusing, so I'm going to use a c in a different spot here. But log base b of x times c is really the same as log base b of x times x times x times x c times. That's what x c means, x times x times x c times. But then based on this property, that's really just log base b of x plus log base b of x plus log base b of x c times. And if you add something up over and over and over and over, you're really multiplying, so it's c times log base b of x, which is that up there. So that's where those properties come from. But what these properties can let us end up with is a very useful new property. Suppose that I have b to the x equals a. Some problem where I'm trying to solve for x. Well, if it's true that the value of b to the x is the same as the value of a, one thing that I can do is take a log of both sides. Because if this statement is true, then this statement must be true. Just take a random log of both sides. The base doesn't actually matter. It's base 10 in this case. Well, now the x can come down in front by that top right property. This just represents some number. I don't know what the number is, but I know it's some number. So I can divide both sides by the log of b. So I divide this side by the log of b, and this side by the log of b. I actually end up with x equals log of b divided by the log of a. So really, I took an exponential function and found a way to write it in a logarithmic form. And we used what I call the all-powerful change of base formula, which is log base b of a equals log of a divided by log of b. Usually when I teach this class, the clouds part and this beam of light kind of shines down, looks sort of like this. And this thing all starts to glow and it gets all magical. It's so powerful and important, the angels kind of sing. I should technically be saying that we can choose any base we want. It could be log base 10, or it could be log base 1000, or log base 2, or whatever. Although there's not really much point to picking bases when we can pick base 10. So just to give a quick example, if we had log base 2 of 3, I can now write that as log of 3 divided by the log of 2, and I can calculate that on my calculator, which I'll show later. I always think the number on the bottom goes on the bottom, the number on top goes on top. So now we can evaluate these logs that are base 10 very simply. Your calculator pretty much only has base 10 programmed into it. That's what this log button right here is. It's doing log base 10 and only log base 10. If I do log base 10 of 12, I get 1.07918, which I'm just going to call 1.079 for now. Here's what that really means. That really means if I convert 10 to the 1.079 ... whatever that is, will equal 12. If I do 10 to the power of my previous answer, 1.07918, I get out 12. So the logarithm function in your calculator has stored all of the solutions to the question 10 to the x equals something. 10 to some power equals some number. It has every single possibility stored. So if I wanted to know, okay, 10 to the x equals 30, well, I would really just want to do log of 10 to the x equals log of 30. The x would come out in front, x times the log of 10 equals the log of 30. And I would divide both sides by log 10. Log 30 divided by log 10. Log 10 is actually 1, for whatever that's worth. I get 1.477. If I do 10 to the previous answer, I get 30. And in the same way, I've had a question like, if you see something like log of 15, that really is asking the question, you're answering the question, 10 to what power equals 15. So if I do log of 15, that's really telling me 10 to the 1.176 equals 15. And so hopefully you can see just how useful this is. I now have log of 2 to the 5th. Well, 2 to the 5th is really 32, and the log of 32 is 1.505. I could have pulled this 5 out in front and then 5 times the log of 2, and you'll see it's actually the same thing. Beautiful. So now I've got log base 4 of 20. Well, some fancy calculators have what's called their log base button. And your log base button, if you can find it, can probably do this in one little push of the button if your calculator's new enough. Mine, however, is not, and even if yours isn't new, it can still handle this, because now I have the change of base formula. This is really the log of 20 divided by the log of 4. Now please understand, that is not the same as the log of 5. Do not ever do that. I can't do 20 divided by 4. And I know there have been times we've just dropped logs, and that sort of seems like a magical thing. That only happens in certain circumstances. Here, I'm going to actually calculate the log of 20 divided by the log of 4. And I get 2.16. Which means it's about equal to 2.16. That means if I do 4 to the 2.16, I'll get something pretty close to 20. And there it is, pretty close to 20. Finally, log base half of an 8. This is a problem that we could do without a calculator by common base. But with a calculator, it's just log of 8 divided by the log of a half. Log of 8 divided by the log of a half. Negative 3, negative 3. Because 1/2 to the negative 3 equals 8 in exponential form. So the change of base formula can do all kinds of useful things. For example, now we can solve these equations. We weren't able to solve this. This is how we started like 4 lessons ago. I asked the question 2 to the x equals 12. And we tried to guess it was around 3.5, 3.6, but we weren't sure. Now, we can take a log of both sides, pull the x out in front, divide both sides by the log of 2, and calculate that. We get 3.584, whatever. I gotta just keep saying about equal to 3.585 also. And if you don't like that, taking a log of both sides and solving that way, another way you can do the same problem, and I actually think this is almost better, is just convert. You can always convert to solve whenever you take a log of both sides. This really becomes log base 2 of 12 equals x. Then I do the change of base formula. Log 12 divided by log 2. So that's exactly what I just did here. Log 12 divided by log 2 is going to come out to the same thing. So if I have 5 to the x plus 1 equals 12 to the x, these numbers don't have a common base. This is how we used to solve these pre-having logs, having a common base. But these numbers don't have a common base. I could put this in log form, or I could take a log of both sides. I'll show how to do it by taking a log of both sides. I mean, the log of 5 to the x plus 1 equals the log of 12, put that kind of high, log of 12 to the x. I can pull these things out in front. When the x plus 1 comes out in front, it really needs to be in parentheses. And that's one whole unit, one whole expression, x plus 1. Now, the way that I best like to do these, there's lots of ways, but I just think of this and this as some number. I don't know what the number is, but it represents some number. So I'm going to find that number. I really get that x plus 1 times the log of 5, which is 0.7 basically, equals x times the log of 12, which is 1.08. And instead of working with these numbers here, I'm going to work with these numbers here that were stored in my calculator. You'll notice I never type in 0.7, I'll always just type in log 5. So log 5 is 0.7 basically. So now I solve this and I have, well, let me go back a little bit. I think I'll do this by estimating first and then show you how to do it more accurately. So I'll show you get all this back. I have this, x plus 1 times 0.7 equals x times 1.08. Well, I can just solve this as an equation. 0.7x plus 0.7 equals 1.08x. Subtract the 0.7x from both sides, and I get 0.7 equals 0.304, 0.38, 1.08 minus 0.7. .08 minus 0.7. Ah, you froze on me. Yeah, it's 0.38. I know it was. So I really have 0.38x equals 0.7. Divide both sides by 0.38. 0.7 divided by 0.38. 1.84. I'm going to check this now. I'm going to come way back up here and check this. I have x equals 1.84. That's an about equal to, so it should be close to equal, but not exactly. 5 to the 1.84 plus 1. Let's see what that equals. 12 to the 1.84. Very, very, very close to each other, just because of a little bit of a rounding error. If I want to do that while keeping my perfect accuracy, instead of making these decimals at this step here, instead of making these decimals, I would have said x log 5 plus 1 log 5 equals x log 12. I would have subtracted the x log 5 from both sides, and I would get log 5 equals x log 12 minus x log 5. And now from here I can factor out the x's. And that I can divide both sides by log 12 minus log 5. So that's log 5 over log 12 minus log 5 equals x. There, we calculate that. So see how close these end up being. Log 5 divided by, in parentheses, log 12, close parenthesis, minus log 5, close parenthesis, 1.838. So it was almost the exact same thing I had here. So you don't have to worry about that if you want to be super accurate. Had this been a 3x, it's just going to become the same game. I'm not really sure why I have this one on here. Maybe I'll skip it. But just to kind of get us started, I'll start by taking a log of both sides. Now I have x plus 1 times log of 5 equals 3x times log of 12. And I just go from there doing the same thing. I would calculate this as some number, calculate this as some number, and work it out. Or keep it a log 12 and go from keeping it a log 12 and a log 5 and just work it out symbolically. I don't think I'm going to finish that one. Here's the last one we'll do. You can ignore this. This is from the previous year. An account pays 8.2% interest compounded monthly. You have 20,000 in the account today. How long do you have 100,000? Well, I can set up this equation. Yes, is that a million? 100,000, sure. 100,000 equals 20,000 times 1 plus, my interest rate is 0.082. I have this thing compounded monthly. And so the question is, how long does this take? We have the x up there as a variable, which makes this more difficult. But I want to try and get the x by itself. The first thing I do is divide both sides by 20,000. That means that 5 equals whatever that is, so let's just work that out. 1 plus 0.082 divided by 12. And ready? 1 plus 0.082 divided by 12. We get 1.0068333 to the 12x. Now, I'm not going to ever round this number. I'll never enter this number into my calculator. I always use this number stored in my calculator. So now I'll convert this into log form. I could take a log of both sides, but if I convert into log form, I get that the log of base 1.00683 of 5 equals 12x. Well, this over here I can calculate. I can do log 5 divided by the log of 1.00683 because that's just the change of base formula. So I'll do the log of 5 divided by the log of the previous answer. So I have that number stored up there already. That's very important. And I get 236.33. That basically means it'll take 236 months for this to happen. For this money to get multiplied by 5, it's going to take 236 months. So I divide that by 12, and it's 19.7 years. It'll take 19.7 years for my money to get quintupled and multiplied by 5. At this point here, we actually knew, we're trying to see how long it takes for the money to multiply by 5. It could be the numbers 100,000 and 20,000, or it could have been the numbers 10 and 2. It wouldn't matter if it takes, the amount of time it takes doesn't matter to multiply by 5. Okay, that should cover today. Thank you.